Hello there. So I'm sure we're excited. More matrices. As I've said, there are 8 lessons and this is lesson 5, so we have been halfway through. In lesson 4, what you were doing, if you can recall, you were looking at equations of planes, putting them into a matrices form and then doing a bit to decide how those planes actually met in real life, whether they met all at one point. What was that called? Can we remember? It was meeting at a unique point. Does it have a name? Not sure. You probably know. And then we looked at ones where they met in a line. So all the 3 planes met in a line, and that was a sheaf. And then the other, when they didn't meet all at one point, then they either formed a triangular prism or they were parallel, etc. Right, so can we recap a bit of that by looking at these 3 planes, writing them in matrix form? Explain how you know none of the planes are parallel. Remember, don't look at the constants on the end, just look at these things as any multiple of each other. That will tell you if they're parallel. And then it says you've got to investigate the intersection of the planes when k is 10 and when k is 12. So basically what you were doing last week, stop this video, have a go, and then I'll flash up the answers. So hopefully pause now. Okay, maybe we've unpaused. Here comes the answers. So the planes are parallel, can be written as a scalar multiple of each other. That is not true in this case, they're not parallel. Right. Then part 2, when k was 10, wrote it in matrix form, it's that. Using a calculator, you find the determinant of that, it's 0. So the matrix is singular, hence the planes do not all intersect at a unique point. So then you have to do a bit of elimination of one of the variables and you get 2 equations. Do they make sense? So when you sub 10 in as the k, do they make sense? Is a big question. And apparently they do. Oops, sorry. So when the constants k is 10, there are infinitely so many solutions because that thing made sense, it was consistent, and so they must be meeting in a straight line, a sheaf. When k was 12, the equations made a bit of nonsense. You can see they're not going to make sense. Try and put them in the calculator, it will say they're no solutions. So therefore, no solutions, since the planes are not parallel, they must be a triangular prism. Okay, so new stuff. Matrix number 5. So if you've got the printout, you can fill it in. If you haven't got the printout, don't want to print it out, you're making your own notes and maybe have to pause as we go along to write things down. So we're understanding what is meant by eigenvalues and eigenvectors. I bet you've been excited about meeting these. And we've also got to understand how to find what's called a characteristic equation and to be able to find eigenvalues and eigenvectors for 2b2s and 3b3s. You'll be glad to hear we're not doing 4b4s. They're cars. So we'll move on. So then, we're going to recap a bit of points and lines, stuff you did last year. I think with Carrie-Anne, see how much you enjoyed these. So a point is called an invariant under a transformation if it maps to, you remember, itself under a transformation. A line is called invariant if every point on the line is mapped to either itself or another point on the line by the transformation. So it's either a point maps to itself or a point maps to somewhere else on the same line. How do we find the invariant points and lines? Well, let's start with invariant points. So invariant points means you times by some matrix M here, there's a 2 by 2, and it stays the same point. Or in 3 by 3, times by some matrix M, 3 points, and they stay the same. Woo. So this example says find invariant points of a transformation with this matrix where K does not equal 0. So we want some, it's a 2 by 2, so it's going to be just an X and a Y. So we want some random X and Y to stay at X and Y. When we times by this matrix, it just gives us X and Y. That would mean it's an invariant point. Right, if we multiply these out, 1 naught, X, Y, that gives me X equals X. And this one you'll get KX plus Y equals Y. Now you can either say, right, it's invariant point, so I want X to be X, so I can see that there. That's good. And you can say, oh, I want Y to be Y, so therefore KX will be 0. So we can take the Y's over if you like there. It's gone. But K, that implies that, and should we do the implies symbol? That implies that KX must equal 0. Now remember, we said here, K does not equal 0. That means that X must be 0. So it implies that X is 0, as K cannot be 0. So invariant points here are when X is 0. Y can be what the heck it likes, but X must be 0. So we'll write that there, invariant points. Points are, let's say, in the form. Right, remember, X can be what the heck, what anything. X has got to be 0, and Y can be whatever it likes. You can call it lambda if you like. So you might want to leave it like that, or you can bring the lambda out and leave it as 0, 1 if you prefer. Be any points there, you can make 2, 3, 4, 5. Lambda can be whatever it likes. Okay, right, next one. Invariant lines. Wow, wow. The invariant lines of transformations with matrix M can be found by substituting X and Y equals Mx plus C in the same equation, in the same equation of line. So I'm going to do that underneath here, but let's just recap that first bit. We'll squeeze it in. You don't have to do this first bit, but sometimes I like to. So we've got this matrix. Find the equation Y equals MC, invariant lines of transformation with this matrix. Right, so invariant points first. If we were, let's squash it up here. 0, 1, 1, 0. Do the same thing. What gives me X, Y that equals X, Y? I always do this bit. So therefore you get Y equals X. If you do it the other way around, you get X equals Y. So you know that the line of invariant points is going to be X equals Y. But there might be some other lines which are invariant, but not a line of invariant points. Drop that one on there if you like. Let's just draw that one there. So this is the line where every point will be mapped to itself under that matrix. Y equals, that's the line of invariant points. Okay, I'll change colour. No, I'll change colour. That'd be very weird, wouldn't it? Change pen colour. Right, let's have a think. Right, so what we're doing, it says we are finding the form Y equals mx plus c, the lines of the invariant lines of the transformation. So what we do here, we've got this matrix, our matrix M, can write small. And we're going to times it by, we're going to put in here a general line. So here we're going to call X is X. x is x, and therefore y, looking at this here, y is mx plus c. So rather than writing y, I'm writing mx plus c. And we need this to map onto the same line. So let's have a look what happens. Let's multiply it out now. So 0 and 1, that gives me, if we change back to, oh, sorry, colour. Not keen on that other colour. Not many colours you can actually see. So here, what do we get when we multiply out this matrix? Well, we get mx plus c, and we get x there. Right, what's been spat out here must also lie on that line y equals mx plus c. So let's write that down. So the answer, I'll put an arrow. So that thing must lie on the line y equals mx plus c. It doesn't have to be the same point, but it can lie on that line y equals mx plus c. So because of that, I'm going to substitute into the equation y equals mx plus c. So here we have y. Now y is x. So x, y equals mx. So we put m, and the x is this thing, isn't it? mx plus c. So y equals mx plus c. Ooh. Now we'll have to expand that out. So we get x equals m squared x plus mc plus c. That is his equation equal to 0. Oh, the wrong thing. That's a c. Oh dear. C plus c minus x. Right. Okay. So what should we do now? We'll try and sort of pull out the x terms. So take x out as a common factor there. We'd have m squared minus 1 lots of x, and we'll have m plus 1 lots of c. So it's now in 0 equals mx plus c. And if you multiply those out, we're going to run out of space here. That's the difference of two squares, isn't it? M minus 1, m plus 1. Okay, right, stop there. Put a line down here. Put a black line. My head's in the way, we're in more maths. Right, so when m equals minus 1, let's see what would make this equation true. If m is minus 1, what we get here, we get 0 equals minus 1, so that's 0, and all those, so we get 0 plus minus 1 in there. Oh yes, we get 0. So that's okay as it is. So what that implies is that c can be anything it likes to be. So here, c, therefore c can be, oops, put the can be anything. And this equation will still be true. So what we've got there then, we've got the line y equals, now m is minus 1, so minus x plus c. Now that's the line of invariance. And you could also bring out this line that we've met before. When m equals 1, what you get then is 0 equals 0 plus 2c. Now here, for that to be true, c must equal 0, no other option. So that's giving me the line y equals just 1m, 1x because x is m is x, 1x plus 0, which brings you back to up there. That's the line of invariance. So that's your line of invariant points. This one, sorry, that's a line of invariant points, and this is just line of invariance. If you can squash that on and write it, line of invariance. So they'll map to different points on the same line, and that's your line of invariant points from up at the top there. If you want to draw that other line in, remember C can be anything. It's -1, not 1, so it's perpendicular to that thing. So C can be 0, or it can be any other of these things here. It could be, as long as we've got a gradient of -1, that doesn't look like very much like 1. Ooh, I'm not very good at this, as we can see. Oh dear. See, these are all perpendicular. And they're all line of invariance. Lovely. So that's just what you did with Carrie Ann last year, really. Nothing new there. Let's see what's coming up. Oh, let's not see what's coming up. Let's give you a turn. So what I want you to do here is find the line of invariant points and find the line of invariance. So you can do that first bit that I did, just to find the line of invariant points if you like, or you just go bang in for that where you replace x is x and y equals mx plus c, and it'll spit out both of those equations, and you can decide which is which. Remember, line of invariant points will always go through 0. So off you go. Have a whirl. Pause the video, and I shall see you in a bit. No chocolate milk left. Right, hopefully now you've unpaused, and here comes the answers. So if you went for that, you would have found the line of invariant points comes out at y equals -3x. So I can write on there, you may, I don't think, he wasn't really asking for this, was it? But you may have said anything of the form lambda equals 1 minus 3 is an invariant point. It did say find the invariant points, didn't it? Ooh, there we go. So that was that. Or if you just went for this next bit, you would have picked it out anyway. Done all that business. 2 and -3. So when it was 2, these all became 0, so it could be whatever it likes. So therefore y equals 2x plus c. I'll get the highlighter out now. So that one is your line of invariance, and that one goes through 0 is the line of invariant points. Super. I'm sure you did a good job of that last year. Right, new eigenvectors and eigenvalues. Wow. Can we hold on the excitement? Damn good, don't they? Anyway, if a square matrix M and a vector V satisfy the equation mv equals lambda v, where v does not equal 0, then v is called the eigenvector of a transformation, and lambda is called the eigenvalue. So this is related to what we're doing, really. M's just a matrix, and we're saying that this v maps to itself, basically, or a multiple of itself. So if that lambda is 1, then it will be a line of invariant, producing points that are invariant. If the lambda is not 1, it'll be making a line of invariance, points that map to another point on the same line. So it's sort of related to what we've just been doing, or what you did in year 12. Right, so example here says a transformation matrix M is represented by that thing. Show that U equals 2, 1 and V equals 3, 1, 3, 5, oh gosh, I can't even read, 3, 4 are eigenvectors. And find the corresponding eigenvalues. So if they're eigenvectors, then they're going to map to themselves or a multiple of themselves. So let's have a see. So we've got here M. We're going to try it with that U1, see what happens, 2, 1. So if we multiply those two out, what do we get? Well, we get 7 times 2 plus 6 is 20. And minus 8 plus 18 is 10. So is that a multiple of that? I think it is. Let's put it out. It's 10 times the original, isn't it? So here, yes, it's an eigenvector because it's gone to a multiple of itself. And the eigenvalue is your lambda, and that's 10. So lambda equals 10, which is the eigenvalue. And that's the eigenvector, the 2, 1. Let's do the same with the second one it's given us and see if that maps to itself or a multiple of itself. Big maths here. 3 times 7 plus 6 times 4. You might need your machine for that. You might be good at mental maths and be shouting 45. Next one is minus 12 plus 4 lots of 18. And that comes to 60, believe it or not. Now, is that a multiple of that? I think it is. If you pull out 15, you will get 3, 4 there. So again, yes, it's an eigenvector because it's multiplied to a multiple. It's been transformed to a multiple of itself. And 15 is lambda equals 15, which is the eigenvalue. So 3, 4 is the eigenvector. 15 is the eigenvalue. Woo! Right, it's a bit strange is this, but never mind. Interesting points or not. If V is an eigenvector, yeah, then the line RTV is an invariant line through the origin. In particular, any multiple of V itself is an eigenvector. So what's that saying? That's a load of old tripe, isn't it? R equals TV. Now we've got a V as an example. I'll use the last example. Let's use the V from the last example. And the V from the last example was the 2, 1. So what we're implying here, and I remember R is a vector, T is just a scalar. So xy equals T lots of 2, 1. And that implies, if you see, just read them across, isn't it? That x equals 2t and y equals t. Now, if you try and eliminate t from that, so therefore, if you look here, t equals x over 2 and t equals y. So if t is t, then this means that y will equal x over 2. And that, interesting enough, is the line of invariance. Line of invariance. That might be the line of invariant points. Note, and that's what I said before in that last thing we were looking at. If lambda actually is 1, and the eigenvector is mapping to itself, and therefore it will be a line of invariant points. Well, right, let's see what's next. Why do we need eigenvalues? Well, real life here. In higher level mathematics, eigenvalues are used in the study of differential equations and also in probability theory. I'll put a video on this, it's interesting. These are huge areas of maths that play prominent roles in engineering. Ooh, what's that new word going to be? Economics. I don't know if you guessed it. E.g., eigenvalues occur naturally in the study of vibration problems, such as for rail tracks and mechanical structures. That's what got you excited, hasn't it? Be similar. Now, how do we work out eigenvalues and eigenvectors if you're not given them? A special method has been developed to solve the important equation. So this is a bit of a blurb. I'll try and explain it a bit more in the gap below. So you've got this equation, some matrix times our eigenvector will give us the same eigenvector or a scalar product of it. And we're told here that V, the eigenvector, cannot be the 0, 0 vector. Not allowed. So it says first it is written as this. Well, what's happened here is that you've got your M, let's do it here, mv equals lambda v. So it's written like this. So we brought this over, mv equals lambda, oh no, not equals, so minus, sorry, minus lambda v equals 0. And then we've pulled out v as a Renzo matrix minus, we pulled out v as a common factor equals 0. You can't just put lambda in here because it's that's a scalar. You have to put it by the identity matrix 1, 0 in order to keep it as a vector there and make sense. Right, so we've got to that situation. So it's first written as this, yes. If the matrix M minus I had an inverse, you could multiply this by the inverse obtaining. If this had an inverse, we could get rid of it, couldn't we? We could put M minus lambda I inverse M minus lambda I V equals 0. That's a 0 matrix time. Oh no, it wouldn't be. Do it first, wouldn't you? Scribble, scribble. M minus lambda I inverse times the 0 vector 0. Right, now if times something by the 0 vector, get 0, and then that'd end up v equaling 0. But that isn't true. Not true. As told, v doesn't equal 0. So basically, that can't be happening. Oh. No, that can't be happening. So if it can't be happening, it means it can't have an inverse. So the conclusion from this must be that M minus lambda I is singular, has no inverse. Oops. This leads to the following method for finding eigenvalues. So if it's no inverse, it's called singular. And if it's no inverse, that means its determinant equals 0. If a matrix has no inverse, it means its determinant is 0. So therefore here, eigenvalues for a matrix M can be found by solving the determinant equal to 0. Right. Let's see. Oh, a bit more summary. An eigenvector V of a matrix M is the direction vector of an invariant line through the origin. When the transformation M is applied to V, the result is a scalar multiple of itself, V. This gives us this equation. For each eigenvector, V, lambda is the corresponding eigenvalue. To find the eigenvectors and the eigenvalues, we solve this determinant equals 0, which is called the characteristic equation of M. Okay, so hopefully you've understood why we're doing that. When you rearrange that equation to try and solve for V, M minus lambda V cannot be 0, it would imply V was 0, so therefore this must be 0, and therefore the determinant must be 0. So find the eigenvalues and corresponding eigenvectors for this matrix. The characteristic equation, solving that. So if we write that down, let me just check what pops up on this slide. Let's fill it in. So 1 minus lambda is on that there, and that minus nothing, it's just that 4 on it, 4 minus lambda, so there we go. So we're solving this equal to 0. So when you find the determinant of something, if you remember what to do there, we times the diagonals and then subtract that diagonal times together, and magically it pops up there. So we're solving this equation equal to 0. So I've got some multiply out some brackets. So that's minus 4 plus lambda minus 4 lambda plus lambda squared minus 6 equals 0. So if you want to turn that equation round so it looks nicer, so we've got lambda squared minus 5 lambda. Is that right? No. Oh, mishap. 3 lambda. Trust myself. And then minus 10 equals 0. And if you factorize that, you'll get lambda minus 5 lambda plus 2 equals 0. So lambda can be one of two things. Lambda can be 5 and lambda can be minus 2. And these are our eigenvalues of M. So we've got the eigenvalues, now we can get the eigenvectors. Let's see. Right, we've got our eigenvalues. And we've got Buster here now to help us. Buster. That's Buster. And Buster? Yeah, Buster's come to help. Right now, so we've got the eigenvalues, we've got to find the eigenvectors. We know this must be satisfied when we times an eigenvector by a matrix. It stays the same eigenvector but a multiple of it, and we've just found that multiple to be 5. So, cup of tea, can't beat it. Right, so let's see what this matrix helps us find. So, so this gives us minus x plus 2y equals 5x, and this one gives us 3x plus 4y equals 5y. Right, Buster's had enough. Ow! It hurts, sweetheart. If you were to rearrange those two equations, what would that give us? well, that would give us 2y. First one will give us 2y equals 6x. Ooh. Therefore, y equals 3x. And on the second one, do we get the same to over there? Yeah, get y equals 3x, don't you? So both can simplify to y equals 3x. So the eigenvector can be any multiple of values. So when x is 1, y is 3. So any multiple of 1, 3. Right, when the other one, we had the eigenvalue of -2. So put -2 in as your lambda. And what does this give us? Well, that gives us minus x plus 2y equals minus 2x. And 3x plus 4y equals minus 2y. So what's the first one giving? Let's give in 2y equals, take that over, add, so that's minus x, isn't it? And therefore y equals minus x over 2. What about this one? Take that over, I'll do it that way. You get 6y equals minus 3x, and if you draw a 6, you get that again, don't you? So they're both giving us y equals minus x over 2. So an eigenvector can be any multiple of, you could pick x as 1, but then y would be a half, and they like whole values. So let's pick x as 2. Pick anything really, as long as that's satisfied. If x is 2, y is minus 1. So your eigenvector can be any multiple of that. Bingo. Done. Cup of tea. Okay, so we've just thought we've done it all, and then they give us a 3 by 3 to do exactly the same with. Got cat hairs in my tea. It's not nice. So finding the eigenvalues first, we solve that thing again, the characteristic equation. The matrix, inverse matrix of that thing can't exist. So it's singular, and therefore the determinant of it must be 0. So there he is. And we've got to do the determinant of 3 over 3. We can't put it in the calculator because it's got lambdas on. So I'm going to multiply it out over the top row. So I've got 3 take lambda, and then we'd have that matrix, wouldn't we? 3 take lambda, 0, 0, 3 take lambda, and then plus 0, won't bother that. So, well, actually minus 0, but plus, and then plus the last one lot of this matrix. And that's got to equal 0. So expanding that one, that times that, minus 0. So it's just actually just, if you want to put another bracket in, 3 take lambda minus 0. And this one plus 1 lot of 0 minus 3 take lambda equals 0. Confusing. Right, so we've got 3 take lambda. If I expand these two, I'd have 9 take 3 lambda, take 3 lambda, so that's 6 lambda, and plus lambda squared. And in here I've just got minus 3 take lambda. Factorise out 3 take lambda. What we're left with? Well, we're left with 9 take 6 lambda plus lambda squared and minus 1. And then we've got right amount in lambda squared minus 6 lambda and minus 8. Now if we try and factorise that, we've got 3 take lambda, and then that one will be, what, 2 factors? This 2 and 4. So lambda, it's actually minus 2 and oh, it can't be, and the plus 8, isn't it? What a wally. Lambda minus 4. That'll do it. So here are our eigenvalues. Our eigenvalues are under there. So I can't get rid of them. I should have written it in there. But the eigenvalues are lambda equals those are our eigenvalues. Eigenvalues. Right. Now to find the eigenvectors corresponding to those three. One can we have? Right, start off with lambda's 2 and get that one. So again, that form at the top is telling us an eigenvector stays the same or a multiple of the same. This time it's a multiple of the same 2 times the same. So what equations does that imply? Well, thankfully there's a lot of zeros here, so not so much. 3x plus z equals 2x. We've also got 3y equals 2y. And we've got x plus 3z equals z. So looking at them, what does that imply? Well, if 3y equals 2y, divide through by y, and then 3 equals 2, that's nonsense, isn't it? So y's got to be 0. And what relationship have we got with x and z? We're looking at that one. We've got x equals minus 2z. And with that one, we've got x equals, take that over, minus z. All right. That can't be right. Oh, I forgot the 2, that's why. Oh, you prat. The 2 should be there. Right, so that's nonsense. And take that over there, just x equals there, it's better. So x equals minus z. So an eigenvalue can be a multiple of, we know that the y is 0. And whatever the x we let, zb must be the negative of it. So I'll pick the easiest number, 1, minus 1. You can pick any number, 2 and minus 2. Super. Right. You could have had minus 1 and 1 if you wanted the other way around. Okay. Right, so for lambda equals 3, what have we got now? Let's change colour pens. You can see a difference here. So we've got 3x plus z. Yeah, about z equals 3x. We've got 3y equals 3y, or at least that's true. And we've got x plus 3z equals 3z. Now, we can see from here, this y can be anything it wants to be, because that always stays true. 3y is 3y. Solving these other 2x. Oh, take them to the top one. That over that just gives me z is 0. And the bottom one, take that over that, gives me x is 0. Ooh. So this time, y can be what it wants. I'll pick 1, but you can pick any number. And the other 2, x and z, must be 0. Spot on. Right. And one more. We had when lambda is 4. So multiply the top line, done that for me. Next line gives me 3y's equals 4y's. Nonsense. And the bottom line gives me x plus 3z's equals 4 z's. Right, I could do a few z's. Right, so y equals 0 from that, because that's a load of more nonsense. And x, take x over there, x will equal z, won't it? Does that satisfy that as well? Yeah, it does, x equals z. So this time, y's got to be 0. If x is 1, z is 1. So anything of that sort, any multiple of that sort will be the eigenvector. And if you wanted to try that and prove to yourself that was working, you could do that matrix on your calculator. Or by hand. What will it give? 3 and 1, that's 4. Not 4. Oh, look, that's 4 times the original. It's all worked. It's just like check for fun. We've not had enough fun already. There we go. So we found all the eigenvectors and their corresponding eigenvalues. Your turn, I think, now. Right, exercise, yeah, 3 of them there. Try these on the big whiteboards, that's your walls at home. Or if you think your parents will spank you for doing that, then maybe try them on a piece of paper and pause this video and then check them in a moment. So please press pause. And then unpause, and here are the answers. Number 1. Number 2. Remember, there can be any multiple of these things, so not one specific answer. And that says 4, 21 and 7. I'm hiding 7. And there I'm hiding, that should be 7, 8, 5. Ooh, sometimes we'll talk about those next lesson actually. When the second independent vector cannot be found, because it gives you just the same answer as that one before. Okay, right. I think that's around about it from me. I think. So you're going to try the worksheet and have fun with that. Or it might be an exercise, can't remember. But you'll see on the homework what it is that you're trying after this. And I shall see you for matrices 6 soon. Bye bye.